October of 1923. Mount Wilson Observatory, California. Edwin Hubble is alone in the dark. The temperature has dropped below freezing. The dome is open to the night sky, and the cold comes in freely. He has been at this for hours, guiding the 100-inch telescope by hand, making small adjustments, waiting for the atmosphere to steady itself long enough to hold the image still. This is the largest telescope in the world, and tonight he is pointing it at something that most of his colleagues consider beneath its dignity. A smudge, not a star, not a planet, a faint, diffuse blur in the constellation Andromeda that any amateur astronomer could find on a clear night if they knew where to look. People had been looking at it for centuries. Persian astronomers wrote about it in the 10th century. Charles Messier catalogued it in the 1700s. Generations of observers had sketched it, measured it, argued about it. And for all of that looking, it remained exactly what it appeared to be: a small, soft, unremarkable smear of light that told you nothing. Hubble is not looking at it with his eyes tonight. He is letting the telescope collect its light over a long exposure, burning it slowly into a glass photographic plate. When the exposure is done, he takes the plate into the small dark room and develops it. Then he looks at what came back. Inside the smudge, almost lost in the texture of the image, there is a point of light he recognizes immediately, not because he has seen it before, but because of what it is doing. It is brightening and dimming in a steady, predictable rhythm, like a heartbeat that never changes its timing. He had found others like it in nearby parts of the sky. He knew the rule that made them useful. The slower the pulse, the more luminous the star in absolute terms. And if you know how luminous something truly is, and you know how bright it appears from where you are standing, the math gives you the distance. He does the calculation. He checks it. He does it again. The star is not inside the Milky Way. It cannot be. The distance is too great. It sits somewhere around 900,000 light-years away, which places it entirely outside our galaxy, out in a region of space that was supposed to contain nothing but empty darkness. Hubble picks up a red pen. On the glass plate, next to the star he has just measured, he writes a single word: "Va." That exclamation point has been talked about ever since, usually as a sign of excitement. But stand in that cold, dark room for a moment and think about what he actually knew in that instant. He was not excited the way you are excited when something good happens. He was shaken the way you are shaken when the ground moves under your feet. Because what that distance meant was not just that this one star was far away. What it meant was that the smudge itself was far away. The entire Andromeda spiral, all that soft, diffuse glow, was not a cloud of gas drifting inside our galaxy. It was something else entirely, something vast and separate and very, very distant. Our galaxy was not the universe. It was one island in something much larger, and the larger universe beyond it did not yet have a clear shape, a reliable scale, or anything close to a number. He had just looked at a smudge and found an entire world beyond the edges of everything humanity had ever mapped. The obvious question followed immediately, the way a second step follows a first. If that smudge is its own separate galaxy, what about the thousands of other smudges scattered across the sky? The catalogues were full of them. Fuzzy patches, soft glows, spiral shapes that had puzzled observers for generations. If Andromeda was its own galaxy, then what were they? That question, simple and almost childlike on the surface, turned out to be one of the hardest questions the universe has ever handed us. 100 years later, we are still working on the answer, and the answer As it turns out, it is stranger than anyone in that cold observatory in 1923 could have imagined. The night before Hubble developed that plate, the universe was a single galaxy, not because anyone had proven it, because no one had proven otherwise. And the mind, given a choice between a bounded home and an unbounded dark, tends to choose the home. That choice had been made carefully, over centuries, by some of the most rigorous minds our species has produced. It was grounded in real observation and genuine mathematical reasoning. And it was wrong in a way that nobody could see. Because the wrongness was not in the details. It was in the frame. The story said this: the universe is made of stars. Our sun is one of them. An ordinary one, sitting inside a vast flat disk of stars that we call the Milky Way. That disk contains everything. Beyond its edges lies darkness. Not darkness hiding something else. Just darkness. Empty space going on without purpose or content as far as physics could reach. The Milky Way was the whole show. When you look at the night sky on a clear, dark night, this story feels completely reasonable. You see stars, only stars. The Milky Way arches overhead as a river of pale light, and everything visible to the eye belongs to it. The planets drift through it. The constellations are drawn from it. Even the faint smudge of Andromeda, barely visible without a telescope, looks like nothing more than a local irregularity. A small cloud of gas, somewhere inside the same structure that contains everything else. The problem was not that people were not curious enough. The problem was that the tools they had could not measure what mattered most. They could see things. They could catalog them. They could describe their shapes and estimate their brightness. What they could not do, for most of the history of astronomy, was measure how far away things were. And without distance, the universe is just a flat projection, a ceiling painted with lights, with no depth and no scale and no way to know whether two objects that appear close together are actually neighbors or separated by an ocean of space. In April of 1920, two of the leading astronomers in the country stood up at the National Academy of Sciences in Washington and argued publicly about the nature of those spiral smudges in the sky. Harlow Shapley argued that the Milky Way was enormous, much larger than most people believed, and that the spirals were relatively small objects drifting inside it. Heber Curtis argued the opposite. He said the spirals were too large and too structured to be anything but independent galaxies, each one a Milky Way in its own right, sitting far beyond the edges of our own. This became known as the Great Debate, and it has been retold many times as a story about two men and two competing theories. The more honest way to read it is as a story about what happens when a genuinely important question cannot be answered by the evidence available at the time. Both men were working carefully. Both had real data supporting their positions. Both were making reasonable inferences from incomplete information. And because neither of them could measure the actual distances to the spiral nebulae, neither of them could prove the other wrong. Shapley was incorrect about the main question. The spirals were not inside the Milky Way. Curtis was right about that. But Shapley was right about the Milky Way being much larger than the consensus believed at the time, which is why some of his arguments made sense given his size estimates. The debate was not clean. The truth was not sitting neatly on one side of the room. What the Great Debate actually demonstrated was the depth of a single gap in human knowledge. Not a gap in cleverness, not a gap in effort, but a specific technical gap. Nobody had a reliable way to measure distances across the vast stretches of space involved. And that one missing piece made an entire category of questions unanswerable. You could argue forever. You could catalog every spiral in the sky and still not know what you were looking at. The map that humanity had drawn of the universe was not wrong because people were not smart enough to draw it correctly. It was wrong because the instruments that would have revealed its wrongness had not yet been built. And the specific instrument that changed everything was not a bigger telescope. It was a mathematical insight buried in data that a woman named Henrietta Swan Leavitt had been accumulating for years. In a job that did not even give her access to the telescopes she was helping to use. The universe did not need a new opinion about itself. It needed a ruler. Henrietta Swan Leavitt did not discover the scale of the universe. She discovered something smaller than that. Something that looked, at the time, like a modest contribution to a very specialized corner of astronomy. She found a pattern in the way certain stars blink. That pattern turned out to be the key that unlocked everything. Leavitt worked at the Harvard College Observatory, starting in the 1890s. Part of a group of women hired to do the mathematical and clerical work of processing astronomical data. The director of the observatory, Edward Pickering, had found that women could be employed at lower wages than men for this kind of painstaking detail work. And so the observatory became home to a remarkable collection of skilled women doing work that was essential to the science without being recognized as science in the way that observation and theorizing were recognized. They were called computers. They measured and catalogued and calculated, working through glass photographic plates that had been taken by male astronomers, using telescopes that the women were generally not permitted to operate themselves. Leavitt was assigned to study variable stars in the Magellanic Clouds, two faint patches of light visible from the southern hemisphere that were understood to be relatively nearby companions to the Milky Way. Working through thousands of photographic plates, she identified hundreds of these variable stars, measuring their brightness at different times and tracking the patterns of how they changed. Among them were a particular type called Cepheid variables. These stars pulsed in a distinctive way, brightening and dimming in a smooth, regular cycle. Some completed their cycle in a few days. Others took weeks. Leavitt noticed something that no one had pointed out before. The Cepheids with longer periods, the ones that took more days to complete one full pulse, were also systematically brighter than the ones with shorter periods. She published this observation in 1908, flagging it as something worth investigating further. In 1912, she published a more thorough analysis, confirming the relationship with precision. The period of a Cepheid's pulse was directly and predictably related to its intrinsic luminosity. A Cepheid that pulsed over 30 days was genuinely more luminous than one that pulsed over 3 days. Always. The relationship held without exception across the hundreds of stars she had measured. A Cepheid variable was a natural measuring tool. If you could find one in a distant part of the sky, you could watch it pulse, read its period, and from the period calculate how intrinsically bright it truly was. Then you could compare that true brightness to how bright it appeared from Earth. The difference between those two numbers tells you exactly how far away it must be. A candle that you know is very bright, seen from far away, appears dim. Measure the dimness. Know the true brightness. Get the distance. Leavitt had given astronomy a ruler that could reach across space. She did not get to see what it measured. She died in December of 1921 from cancer. 2 years before, Hubble used her method to determine the distance to Andromeda. There is a story that the Swedish mathematician Gustav Mittag Leffler, looking to nominate her for a Nobel Prize in the early 1920s, wrote to the Harvard Observatory to inquire about her work and was informed by Pickering's successor that she had died. The Nobel Prize is not awarded posthumously. Her name does not appear on the discovery that her work made possible. This is sometimes told as a story about injustice, and the injustice was real. But there is something in it that goes beyond fairness or recognition. Something that has to do with how ideas move through the world, independent of the people who generate them. Leavitt was not working toward a revolution in cosmology. She was working toward accuracy in a catalogue, toward doing her job well in a room full of glass plates. With a magnifying loupe and a pencil, and the kind of focused attention that produces real knowledge, without any guarantee that the knowledge will go anywhere. She found a pattern in blinking stars. She documented it carefully. She had no way of knowing that the pattern she was recording in the Magellanic Clouds would become the foundation of the most consequential distance measurement in the history of science. And then, it went everywhere. Hubble used her period luminosity relationship to calculate the distance to the Cepheid he found in Andromeda. His initial figure, around 900,000 light-years, was lower than the true distance, which we now measure at about 2.5 million light-years. The gap came from a calibration issue that the astronomer Walter Baade would not resolve until 1952, when he discovered that there are actually two distinct populations of Cepheid variables with slightly different period luminosity relationships, and that Hubble had been using the wrong calibration for extragalactic distances. It was not a mistake Hubble could have caught with the tools available to him at the time, but even the underestimate was enough. 900,000 light-years placed Andromeda so far outside the Milky Way that there was no longer any way to argue it was a local object. The universe was not a single galaxy. It was a collection of galaxies, and the ruler that measured the first one was a pattern in blinking stars, found by a woman working through photographic plates in a Cambridge building, recorded in a catalogue that carried her name for years before anyone fully understood what it had actually measured. Once Andromeda fell into place, the rest followed quickly, not because anyone immediately went out and measured all the other spirals. Measuring a single Cepheid variable required weeks of careful observation and calculation. Doing the same for thousands of objects scattered across the sky was not a project that could be finished in a season or a decade. But the logic did not require every measurement to be made individually. Once it was established that Andromeda, the nearest and brightest of the spiral nebulae, was a galaxy in its own right, sitting far beyond the Milky Way, the implication for every other spiral nebula in the sky was immediate. They were the same kind of thing, and there were thousands of them. The catalogues that astronomers had been building for 2 centuries without fully understanding what they contained suddenly read like a different document. Charles Messier had compiled his list in the 1700s because fuzzy patches kept fooling him into thinking he had found a comet. He wanted to mark them so he could ignore them when they appeared in his eyepiece. The list he built to dismiss objects that were not comets turned out to contain some of the most significant structures in the observable universe. Many of the fuzzy objects Messier had catalogued were galaxies, each one a vast system of hundreds of billions of stars, sitting at distances that human intuition had not been built to comprehend. He had been cataloguing them while looking for something else entirely, without any way to know that what he was setting aside was larger and more distant than anything he was searching for. The New General Catalogue, published in 1888 by John Louis Emile Dreyer, listed nearly 8,000 nebulae and star clusters. Some were clouds of gas within our own galaxy. Some were star clusters. But many of those catalogue entries, the spiral and elliptical shapes that astronomers had spent decades puzzling over, acquired a new identity after Hubble's measurement. Not a cloud, not a curiosity, a galaxy. The catalogues had been listing them for decades. It just took until 1923 for anyone to understand what was being listed. Hubble himself spent the years that followed measuring more of them. He classified their shapes, divided them into spirals, ellipticals, and irregulars. built the first coherent taxonomy of galaxies as a category of object. And along with his colleague Milton Humason, he documented something even more startling than the mere existence of other galaxies. Almost all of them were moving away from us. The further away a galaxy was, the faster it appeared to be receding. The universe was not static and unchanging. It was expanding, carrying galaxies apart from each other, the way raisins in a rising loaf of bread are carried apart by the dough swelling between them, every raisin drifting away from every other. That expansion, once understood, added a new dimension to the question of how many galaxies existed. Because if the universe is expanding now, and you run that expansion backward in time, it must have been smaller in the past. Much smaller, dense and hot and compressed, in a state from which it erupted into the expanding cosmos we now inhabit, which means the universe has a history, a beginning, an age, and light traveling at a fixed speed through that expanding space has had only a limited amount of time to travel since that beginning, which means there is a horizon, a distance beyond which we simply cannot see, not because of any limitation in our instruments, but because the light from that distance has not yet had time to reach us. The question of how many galaxies exist was already running into a structural problem in these early years after Hubble's discovery. It was not just a question of counting. It was a question of what could possibly be counted. Given the physics of light and time and the age of the cosmos, the visible universe had a boundary, and nobody knew how many galaxies lay beyond it. And all of this was being learned from inside one of those galaxies. Not from above the universe, not from some neutral vantage point outside the system, from within one spiral arm of one ordinary galaxy, using light that happened to arrive here, on one planet. At one moment in time, the count had barely begun, and already the counter was standing inside the thing being counted. The telescopes of that era could see only the brightest, nearest galaxies. Beyond a certain distance and a certain level of faintness, the technology ran out. The universe faded into noise before it ran out of galaxies, and there was no way to know how much was hiding in that noise. That situation would not change in any fundamental way until a decision was made. In the 1990s, to point the most powerful space telescope ever built at a piece of sky that appeared to contain absolutely nothing. In the fall of 1995, Robert Williams was about to do something that made a lot of his colleagues uncomfortable. Williams was the director of the Space Telescope Science Institute, the organization responsible for managing the scientific use of the Hubble Space Telescope. In that role, he had something valuable and finite, a small allocation of observing time that was his to assign, without going through the normal proposal and review process. Every other researcher who wanted time on Hubble had to submit a proposal, survive a competitive review, justify their science against hundreds of other requests from astronomers around the world. Williams had a portion of time set aside specifically for the director to use at his own discretion. It was meant for things that fell outside the normal categories, ideas that were hard to evaluate by conventional standards. He had decided to use it to stare at nothing. A specific patch of sky near the handle of the Big Dipper that had been examined and found to contain no bright stars, no known galaxies, no catalogued objects of any significance. A region chosen, in part, precisely because it was boring. It was as close to a blank piece of sky as could be found in a direction away from the obscuring dust of the Milky Way's plane. If you were going to look deep into the universe without the galaxy's own structure cluttering the view, you wanted a window like this one, and the plan was to keep Hubble's eye fixed on that window for 10 consecutive days. 10 days of observing time on Hubble was not a small thing to spend. The telescope was in constant demand. There were proposals from planetary scientists, stellar astronomers, cosmologists, people studying black holes and supernovae and the chemical composition of distant quasars. Hundreds of legitimate, carefully designed programs competed for every available hour. To take 10 days of that time and point it at a blank spot was, to some people, an act bordering on irresponsibility. Williams heard the objections. Some colleagues told him directly that it was a waste. Others were more diplomatic, but made clear they thought the time could be better spent on targets with a guaranteed scientific return. The blank patch of sky might reveal interesting things, or it might reveal nothing at all. If it revealed nothing, that was 10 days gone, with nothing to show for it except a very detailed image of empty space. He went ahead anyway. The reasoning was straightforward, even if the outcome was uncertain. Every time a more powerful telescope had been turned toward a region of sky that previous instruments found unremarkable, something had been there. Not always what anyone expected, but something. The universe had a consistent track record of filling in spaces that earlier technology had read as empty. Williams was betting on that track record continuing. He was betting on the same thing Hubble had bet on 72 years earlier in the cold on Mount Wilson, that the universe had put something in the dark, and that a good enough instrument, pointed in the right direction, for long enough, would find it. The telescope observed the target field from December 18th through December 28th of 1995, accumulating light over 342 separate exposures that were later combined into a single image. The data was released publicly on January 15th of 1996. Within hours of its release, it had gone around the world. That tiny patch of sky, chosen because it contained nothing, contained nearly 3,000 galaxies. Not stars, galaxies. Each one a system of hundreds of billions of stars, some showing up as elegant spirals, some as smooth elliptical glows, some as irregular smears of light from the early universe when galaxies had not yet settled into the forms we recognize today. Some of the objects in the image had been traveling toward that camera for more than 12 billion years. The light that registered on the detector had left its source when the universe was less than 2 billion years old, long before the Earth existed, long before the solar system existed, in an era of cosmic history that no human instrument had ever directly observed before. The image became known as the Hubble Deep Field, and what it did to astronomy was not simply add to a count, it changed what the darkness meant. Before the deep field, the darkness between visible objects was understood as absence. Space was mostly empty, and the galaxies were the exceptions. The populated islands scattered through the void. After the deep field, that understanding reversed itself. The darkness was not empty. It was full. Every patch of sky that looked blank to every instrument that had previously examined it was at sufficient depth, teeming with galaxies. The emptiness was not a fact about the universe. It was a fact about the limits of what we had been able to see. It was not a discovery of a special place. It was the discovery that no place was special enough to be empty. Williams had not found 3,000 galaxies by building a better telescope or developing a more sophisticated technique. He had found them by looking longer, by holding still in one direction and letting light accumulate that had been traveling toward that spot for billions of years, waiting for an instrument sensitive enough to catch it. The galaxies had always been there. They were there before the telescope was launched, before any human being had set foot on the moon, before any radio signal had been broadcast from Earth. They were there when that light left them, 12 billion years ago, heading in our direction without knowing that anything would eventually be here to receive it. 3,000 galaxies in a patch of sky the size of a grain of sand held at arm's length. The implications of that number took a moment to land. And then they were staggering. The Hubble Deep Field covered a tiny fraction of the total sky. If that fraction was at all representative of other directions, then multiplying the galaxy count by how many such patches it would take to tile the entire celestial sphere should give a rough estimate of the total galaxy population within reach of a telescope of Hubble's depth. Williams knew this. His team knew it. The calculation was done quickly, and the number that came back was the one that would anchor public understanding of the universe's scale for the next 2 decades. Somewhere around 200 billion galaxies. In the observable universe alone, the darkness was not empty. It had never been empty. It had just been waiting for someone patient enough to look. 200 billion. Say it out loud once, and let the words sit there before reaching for the next sentence. 200 billion galaxies, each one containing hundreds of billions of stars. All of them inside the portion of the universe our instruments could reach in 1995. If you tried to count them 1 per second without ever sleeping, you would need longer than the current age of the universe to finish. For a while, that number felt like an answer. It spread through textbooks and documentaries and classroom posters. The universe contains 200 billion galaxies. Clean, large, appropriately humbling. The kind of number that makes a person feel small in a way that somehow also feels good. The danger of a beautiful calculation is that it can feel more final than it really is. The number 200 billion was never quite what it appeared to be. The arithmetic that generated it was clean on the surface and full of quiet assumptions underneath. And those assumptions were doing a tremendous amount of work without announcing themselves. The logic went like this. Take the Hubble Deep Field image. Count the galaxies in it carefully. Measure the fraction of the total sky that the image covers. Divide the full sky area by that fraction to find out how many deep field patches it would take to tile the entire celestial sphere. Then multiply the galaxy count from 1 patch by that number. That gives you the total population extrapolated across the observable universe. It is the same logic you would use to estimate the number of fish in a lake by counting what turns up in one small net and scaling up. Reasonable, practical, and dependent on one critical assumption that the small sample looks like the whole. For galaxies visible to Hubble at the depth of the deep field, this assumption holds up reasonably well. The universe on very large scales is thought to be roughly the same in every direction. No patch of deep sky is dramatically different from any other. That has been tested with additional deep fields pointed at different parts of the sky. And the results are consistent enough to trust the multiplication. But there is a second assumption buried inside the number. Quieter and more consequential. One that the deep field arithmetic never addresses. The assumption that the galaxies Hubble could detect represent the galaxies that exist. Those are not the same assumption. The first is about where galaxies are. The second is about which ones show up. Hubble could see galaxies down to a certain level of faintness. Below that level, galaxies did not disappear from the universe. They disappeared from the image. The detector had a sensitivity limit, and anything too faint or too distant or too small to push light above that limit simply was not there as far as the data was concerned. The galaxies most likely to fall below that limit are not the big bright spirals. Those show up easily. The ones that vanish into the background are the small ones. The faint ones. The dwarf galaxies that contain far fewer stars than the Milky Way and shine with correspondingly less light. And the universe produces vastly more small galaxies than large ones. For every galaxy the size of the Milky Way, there are many more smaller, dimmer structures, collections of stars that qualify as galaxies by every reasonable definition, but produce only a fraction of the light that the obvious spirals produce. 200 billion was a count of everything Hubble could see. It was never a count of everything that existed. There was also a third complication that the simple multiplication did not account for. A deep field image is not a photograph of one distance. It is a stack of distances, a column of space stretching from the relatively nearby universe all the way back to the earliest galaxies. Each layer from a different era of cosmic time. The galaxies in the image are not all contemporaries. Some formed recently. Some are remnants of the very early universe. Counting them all in a single frame and treating them as a simultaneous population is a bit like photographing a busy street over 100 years and counting every person who ever walked through. The count reflects time as much as it reflects space. 200 billion was a real number, produced by real observations and real arithmetic. It captured something true about the scale of the observable universe. But it was a snapshot taken with one particular instrument at one particular depth, reporting only what that instrument could see. 200 billion was the answer the universe let us find first. It was not lying. It was just showing us the part it had decided, without asking our opinion. To illuminate. A star cluster and a dwarf galaxy can look, at first glance, like two versions of the same small thing, a loose gathering of stars held together by gravity. One counts as a galaxy, the other does not. The difference sounds obvious until you try to draw the line. The working definition that most astronomers use goes something like this. A galaxy is a gravitationally bound system of stars. Gas, dust, and dark matter, held together by its own gravity, large enough to have its own structure, and embedded within a halo of dark matter that distinguishes it from a simple star cluster. That definition sounds solid until you try to apply it to the actual objects scattered across the sky. And then it starts to flex in ways that matter enormously for any attempt at counting. Start with something close to home. The Milky Way has two small companion structures visible from the southern hemisphere: the Large Magellanic Cloud and the Small Magellanic Cloud. They look like detached pieces of our own galaxy. Faint, glowing patches that sailors used for navigation for centuries. Astronomers classify them as dwarf irregular galaxies, separate systems in their own right, gravitationally bound to the Milky Way, but distinct from it. By most definitions, they count as galaxies. Two of them, right there, orbiting us. But the Milky Way also has dozens of other satellite structures, smaller and fainter, discovered mostly in the last 2 decades as survey technology improved enough to detect them. Some are clearly dwarf galaxies by any reasonable definition. Others are much harder to classify. They have so few stars, spread over such a diffuse area, that the line between a very faint dwarf galaxy and a large, loosely bound star cluster becomes genuinely blurry. Astronomers argue about individual objects in this category. There is no bright line in nature that separates galaxy from not galaxy at the faint end of the scale. There is a continuous spectrum of stellar systems ranging from large and obvious down to small and ambiguous. And where you draw the boundary determines how many galaxies you are counting. This is not a minor technical detail. It has real consequences for the total number. Consider what happens when 2 galaxies collide. The Milky Way and the Andromeda Galaxy are moving toward each other right now, drawn together by mutual gravity. And in roughly 4 billion years, they will begin a collision that will play out over hundreds of millions of years. During that process, the 2 spiral structures will interpenetrate, distort, fling stars into long tidal streams, and eventually settle into a single merged system. At the moment of first contact, You have two galaxies. At the end of the merger, you have one, somewhere in between. The question of how many galaxies exist in that particular region of space does not have a clean answer. The count is changing, and it is changing, not because galaxies are being created or destroyed, but because two things that were separate are becoming one thing. And the definition of separate is doing work that the definition was not designed to handle. This is happening constantly throughout the universe. Galaxies merge. They always have. The Milky Way itself is the product of many ancient mergers, having absorbed smaller companion galaxies over billions of years. Every large galaxy in the universe has a similar history. The count of galaxies at any given moment is not a fixed inventory. It is a snapshot of a process that has been reducing the total number of individual structures since the early universe. As small galaxies fall into larger ones and cease to exist as independent systems, then there are the objects at the extreme ends of the size distribution that challenge the definition in different ways. At the large end, there are giant elliptical galaxies sitting at the centers of massive galaxy clusters. Structures so enormous that they stretch across millions of light years and contain the equivalent of tens of trillions of solar masses in stars. These objects grew to their current size by consuming smaller galaxies over billions of years. In some cases, the boundary between the giant central galaxy and the diffuse stellar halo surrounding it is not a sharp edge, but a gradient. Stars becoming gradually less dense as you move outward, with no obvious stopping point. When does the galaxy end and the space between galaxies begin? The answer involves a judgment call. At the small end, there are ultra-faint dwarf galaxies discovered in recent years around the Milky Way that contain only a few thousand stars. A few thousand stars sounds like a lot until you compare it to the hundreds of billions in a galaxy like our own. These objects have so little mass in visible stars that they would be invisible from any significant distance. We can detect them only because they are practically next door. If structures like these exist around other galaxies, and the models strongly suggest they do, they exist in numbers that dwarf the count of easily visible galaxies. But from any distance greater than our immediate neighborhood, they are undetectable. The number of galaxies in the universe is not a fixed quantity waiting to be measured. It is a number that depends on a definition. And the definition has soft edges that expand or contract the number significantly, depending on how strictly they are applied. Count only objects above a certain luminosity threshold, and you get one number. Count every gravitationally bound stellar system with a dark matter halo, and you get a much larger number. Nature did not build galaxies in neat, countable units. It built a continuous distribution of stellar systems ranging across many orders of magnitude in size, luminosity, and mass. And the word galaxy is a label that humans have applied to part of that distribution. The label is useful. It captures something real. But the edge of the label, the place where galaxy becomes something else, is a human decision and not a natural boundary. Every count of galaxies is, in part, a count of how we have chosen to draw a line. And that line, it turned out, was going to become even more consequential when astronomers began to grapple seriously with the galaxies that no telescope could see at all. Picture a concert hall filled with musicians playing at full volume. You are standing outside, 2 blocks away. What you hear through the walls and the distance is not nothing. But it is not the concert either. It is the loudest instruments, the bass notes that carry furthest, the occasional burst of brass cutting through the brick. The violins are in there. The woodwinds are in there. But from where you are standing, they are below the threshold of what the street noise and the distance will allow you to hear. The observable universe works something like that. What our telescopes detect is not the full orchestra. It is the portion of the universe playing loudly enough to register across the distances involved. In 2016, a team of astronomers led by Christopher Consolis at the University of Nottingham published a paper that revised the galaxy count in a way that got a lot of attention. They were not reporting a new observation. They were doing something harder and more interesting than that. They were trying to figure out how wrong the existing count was, and by how much, and why. The method they used involved taking the deep field images and converting them into something more than a flat picture. They built three-dimensional maps, sorting the galaxies not just by their position on the sky but by their distances, which correspond to different moments in cosmic time. Looking further into space is looking further back in time. And the further back you look, the younger the universe you are seeing. By mapping the galaxies this way, Consolis's team could study how the galaxy population had changed across cosmic history. What they found was a pronounced pattern. The early universe, the universe as it existed billions of years ago, was packed with small galaxies. Far more of them, in a given volume of space, than exist in that same volume today. This made sense in the context of what astronomers already understood about how galaxies evolve. Small galaxies do not stay small forever. They fall into larger ones, to merge with each other, get consumed. The process of assembly, where small structures build up into larger structures over time, predicts exactly this kind of pattern. More numerous small galaxies early on, fewer but larger galaxies as the universe ages and mergers accumulate. But the pattern revealed something else as well. When Consolis's team looked at the early universe in the deep field data, they were seeing only the galaxies bright enough to register on the detector. The faintest small galaxies, the ones that the telescope could not quite detect, even with long exposures, were simply absent from the maps. And their models of how galaxy populations should evolve told them that those absent galaxies had to be there. The numbers did not add up unless there was a substantial population of galaxies too faint to see. They worked backward from the math. How many faint galaxies had to exist to produce the population of larger galaxies visible today? Given what we know about merger rates and galaxy evolution, the answer was striking. For the observed numbers to make sense across cosmic time, the actual galaxy population had to be far larger than the observable one. Their best estimate was that the vast majority of galaxies in the observable universe were too faint and too distant to be detected by any telescope then in existence. That estimate pointed toward a total population closer to 2 trillion, roughly 10 times the previous figure of 200 billion. 2 trillion, a 2 followed by 12 zeros. 10 times the previous best estimate. The majority of it hiding in the dark below the detection threshold of every instrument humanity had ever built. The more important thing about this revision is not the number itself. It is what the number implies about the enterprise of counting galaxies in the first place. Every survey of the sky, every deep field image, every three-dimensional map of the galaxy distribution, every statistical analysis of how galaxies cluster and evolve, all of it has been built on data that captures only the brightest fraction of the actual population. The invisible majority is not a minor correction at the margins. It is the dominant feature of the real universe. The part that is structurally out of reach for any instrument that depends on receiving visible light from objects at cosmological distances. The universe hides the majority of its galaxies not with walls or dust or any dramatic mechanism. It hides them simply by making them faint, and then placing them far enough away that faint becomes invisible. The darkness in a deep field image is not emptiness. It is the combined glow of galaxies too dim to resolve individually, blended into the background noise, present but unreadable. like a conversation happening just below the threshold of hearing in a room you cannot enter. 2 trillion galaxies in the observable universe. That number replaced 200 billion as the headline figure after 2016. But both numbers share the same fundamental limitation. They are counts of what we know about, or what we can model from what we know about. The universe does not stop at the edge of what our models can reach. The galaxies that exist beyond the reach of our models are not arranged randomly in the dark. They are organized. They have been organized since before the first star ever burned. And the structure they are organized into is something that no survey had predicted, and every survey since has confirmed the universe is not a fog. It is a web. And the web was built before there was anything to weave it. On a clear night in the Arizona desert, far from any city, the Milky Way stretches overhead as a river of light so dense it casts faint shadows on the ground. From that same spot, if you know exactly where to look, you can find Andromeda with your naked eye. A small gray smudge near the zenith. 2 galaxies visible at once. The one you are standing inside, and one you are looking across 2.5 million light-years to reach. It feels like a lot of space between them. By the standards of what astronomers discovered when they began mapping the large-scale universe, Andromeda and the Milky Way are practically touching. When surveys in the 1980s and 90s began charting the positions of tens of thousands, then hundreds of thousands of galaxies across the sky, the expectation going in was a more or less uniform distribution. Galaxies clustered in groups and clusters. Yes, because gravity pulls things together, but spread more or less evenly across the large-scale landscape of space. What they found instead was something nobody had predicted with any confidence. The galaxies were arranged in a web. Long filaments of galaxies stretched across hundreds of millions of light-years, like threads of silk in an enormous 3-dimensional fabric. At the intersections of those filaments, galaxies piled up into massive clusters. Concentrations of hundreds or thousands of galaxies packed into regions that were dense by cosmic standards. And between the filaments and clusters, separating them from each other, like the empty spaces between the strands of a spider's web, were voids. Enormous regions of near-nothingness, volumes of space, hundreds of millions of light-years across, containing almost no galaxies at all. This structure, which astronomers came to call the cosmic web, was not a minor feature of the universe. It was the dominant feature. The universe, on its largest scales, was not a uniform fog of galaxies. It was an intricate network of dense threads surrounding hollow emptiness, like foam, frozen into a structure the size of everything. The voids are harder to talk about than the filaments because they are defined by absence. But they are real, and they are immense. A galaxy sitting near the center of one of the largest known voids would look out into a sky almost entirely empty of neighbors. In every direction, the nearest other galaxies would be hundreds of millions of light-years away, faint and sparse at the edges of vision. That civilization would have no way to know that, just over their observable horizon. The filaments of the cosmic web were dense, with galaxies clustered tightly together. Their census of the universe would look almost nothing like ours. This is not a hypothetical concern. Where you are in the web determines what you can see. And what you can see determines what you count. The Milky Way sits in what cosmologists call the local group, a modest collection of a few dozen galaxies dominated by us and Andromeda, with a population of smaller dwarf companions orbiting both. The local group is itself part of a larger structure called the Laniakea supercluster, a concentration of galaxy groups and clusters spanning roughly 500 million light-years that was only fully mapped in 2014. Laniakea contains the mass of roughly 100,000 galaxies like our own. And Laniakea is itself just one node in the broader cosmic web, connected to other superclusters by the filaments of the web and separated from them by voids. We are not in a particularly crowded part of the universe. We are somewhere in the middle, in a modest cluster at the edge of a supercluster, with the cosmic web extending in every direction as far as surveys have been able to reach. What this means for the count is subtle but important. The 2 trillion galaxies estimated to exist in the observable universe are not spread uniformly through that volume of space. They are concentrated into the filaments and clusters, leaving the voids nearly empty. The average density, smeared across the whole observable volume, gives you the 2 trillion figure. But the actual distribution is lumpy in a way that the average completely obscures. Most of the volume of the observable universe contains almost no galaxies. Most of the galaxies are packed into a small fraction of the total volume. Counting galaxies without understanding the web they live in is like counting the population of a country by sampling randomly from a map, without knowing that most of the people live in cities that cover a small fraction of the land. The sample and the structure are 2 different things, and confusing them produces numbers that are accurate in one sense and deeply misleading in another. The Milky Way feels enormous because we live inside it. But in the architecture of the cosmic web, it is not a continent. It is a lit window in one building, on one street of a city whose full map no one has yet seen. The web extends beyond it in every direction, holding structures so vast and so numerous that the 2 galaxies visible to the naked eye from that Arizona desert are less than a rounding error in the total count. They are real. They are there. They are the part of the web you can see with your own eyes. On a clear night, if you know where to look, the rest of the web is there too. You just need to know that it is. And the thing that built it, the scaffolding that determined where every filament would form and every void would open, was something no survey has ever directly seen. Long before the first star ever burned, the universe was already building the framework that would determine where every galaxy would eventually form. You cannot see this framework. Nobody can. It does not emit light, absorb light, or interact with light in any way that any instrument has ever directly detected. What it does is pull. It bends space. It gathers ordinary matter toward itself through gravity, organizing the raw material of the cosmos into the structures that would eventually collapse into stars and galaxies and everything built from them. It outweighs all the visible matter in the universe by a factor of roughly 5 to 1. And we do not know what it is. We call it dark matter, which is less a description than an honest admission of ignorance. We know it exists because of what it does. Galaxies rotate at speeds that cannot be explained by the gravity of their visible stars and gas alone. Galaxy clusters bend the light passing through them more strongly than their visible mass should allow. The large-scale structure of the cosmic web, the filaments and voids that surveys revealed in the 1980s, could not have formed from ordinary matter alone in the time available since the beginning of the universe. Something with much greater mass had to be there first, providing the gravitational wells that ordinary matter fell into. Dark matter is not a hypothesis astronomers invented to save a theory they liked. It is the conclusion forced by many independent lines of evidence, each one pointing to the same answer from a different direction. There is more matter in the universe than we can see, and the matter we cannot see outweighs the matter we can by a wide margin. In the very early universe, dark matter was not perfectly smooth. There were regions slightly denser than their surroundings. Tiny fluctuations left over from processes in the first moments after the beginning. Gravity amplified those fluctuations over time. Denser regions attracted more matter, which made them denser still. the dark matter collapsed into filaments and halos, creating the invisible scaffolding of the cosmic web before a single star had ever ignited. Then, ordinary matter, following the gravitational pull of the dark matter structures, fell into those halos. Gas compressed, heated, and eventually reached the densities needed for fusion to begin. The first stars formed. Those stars gathered into the first galaxies. The galaxies organized themselves along the dark matter filaments, clustering at the nodes where the filaments intersect, staying sparse in the voids where the dark matter was thin. Every galaxy in the observable universe, every spiral and elliptical and dwarf irregular that has ever been catalogued or counted or photographed, formed because dark matter arranged itself into a halo first. The galaxy is, in a real sense, the visible surface of a much larger dark matter structure. The stars and gas and dust that we can see are the small, luminous component. The dark matter halo surrounding each galaxy extends to distances many times the radius of the visible galaxy, containing most of the total mass of the system while contributing nothing to its light. This creates a problem for counting that goes deeper than the visibility issues of the previous chapters. When we count galaxies, we are counting the luminous components of dark matter halos. But not every dark matter halo contains a luminous galaxy. Simulations of the universe's structure predict that there should be many more dark matter halos than there are visible galaxies. Small halos, below a certain mass threshold, may never have accumulated enough ordinary matter to form stars at a detectable level. They exist as gravitational structures in the dark, places where a galaxy could have formed, without ever lighting up. If that inference is correct, and the evidence from simulations is substantial, then the question of how many galaxies exist has an answer that depends on whether you are asking about visible galaxies, or about all the dark matter structures that could in principle host a galaxy, or about some intermediate category of partially luminous systems that may or may not qualify as galaxies by conventional definitions. Each of those is a different question with a different answer. All of them are asking about the same universe. We are counting the light. The universe built the darkness first. The light is what happened in some of the dark places when conditions were right. The darkness is the structure. The galaxies are what the structure allowed to illuminate itself. And the count of galaxies will always be a count of the lit portions of an architecture we can only trace in outline, through the effects it has on the things we can see. The most powerful instrument ever built to push that outline further was launched on Christmas Day of 2021. What it found in the dark, in the earliest light the universe ever sent us, was not what anyone had prepared for. On Christmas Day of 2021, a rocket lifted off from the Guyana Space Center on the northeastern coast of South America, carrying the most complex scientific instrument ever built into space. The James Webb Space Telescope had been in development for over 2 decades. It had survived budget crises, technical failures, and a launch delay that stretched across years. When it finally reached its destination, a gravitationally stable point about 1 million miles from Earth, and unfolded its golden mirror in the cold, dark, the astronomical community held its breath. The mirror was coated in a thin layer of gold, because gold reflects infrared light with exceptional efficiency. And infrared light was what Webb was built to see. This mattered because of something that happens to light as it travels across the expanding universe. When a galaxy is very far away, the light it emits has to travel for a very long time to reach us. While that light is traveling, the universe continues to expand. The expansion stretches the wavelength of the light, shifting it toward the red end of the spectrum and then beyond, into the infrared range. The most ancient galaxies, the ones that formed when the universe was only a few 100 million years old, have had their light stretched so dramatically that none of it remains in the visible range at all. Hubble could not see those galaxies clearly. Webb could. The scientific community had specific expectations for what Webb would find when it turned its infrared eye toward the deep universe. Those expectations were not guesses. They were the output of decades of theoretical work, computational modeling, and careful inference from the observations that previous telescopes had made. The models predicted that the very early universe should contain small, dim, chemically primitive galaxies just beginning to take shape. Young structures, barely assembled, with few heavy elements, because those elements are forged in stars, and the first stars had not yet had time to live and die and scatter their products across the cosmos. Webb looked, and what it found was not what the models had prepared anyone to see. The galaxies at the frontier of cosmic time were more luminous than expected, more structured than expected. Some of them appeared to have assembled their stars more efficiently than the simplest versions of the models had predicted. Heavy elements were present in amounts implying multiple generations of stellar evolution had already occurred. These galaxies did not look like embryos. Some of them looked more developed than their age seemed to allow. The surprise is not that galaxies existed early. Everyone expected that. The surprise is how quickly some of them became luminous, massive, and chemically interesting. 1. Galaxy, designated JADE-SG-SZ140, was confirmed to exist when the universe was only about 290 million years old, making it among the most distant objects ever observed. Its light has been traveling for more than 13.5 billion years to reach Webb's mirror. What made it remarkable was not simply its distance. It was the fact that it was already large, already luminous, already showing signs of chemical complexity at a time when the universe had barely begun. The rate at which it appeared to have assembled its stars was faster than the prevailing models had suggested was typical for that era. Then Webb found something even further out. A galaxy designated MOMZ-14 was confirmed at a still greater distance. Seen when the universe was approximately 280 million years old, 280 million years into a 13.8 billion year history. At that age, according to the models that had guided astronomical thinking for decades, galaxies were just beginning to flicker into existence as dim, fragile, barely. Their structures. What Webb found was more developed than that picture suggested. And scattered throughout these deep field observations were objects that generated some of the most intense discussion in the astronomical community since the original Hubble Deep Field images of the 1990s. Small, intensely red points of light appearing in surprising numbers across the early universe. They were promptly nicknamed little red dots. Nobody is entirely sure what they are. Some researchers propose they are extremely compact young galaxies undergoing furious bursts of star formation. Others suggested they are active galactic nuclei, galaxies whose central black holes are consuming material at extraordinary rates and blazing with the energy of that consumption. Still others proposed combinations of both, or something not yet fully characterized. The debate about little red dots is active and unresolved. Papers continue to appear. Each new analysis sharpens some aspects of the picture while leaving others genuinely uncertain. Webb did not prove that our fundamental understanding of cosmology is wrong. The core framework is the picture of structure growing from dark matter seeds, gas cooling into halos, stars igniting and assembling into galaxies, remains well supported by the overall body of evidence. What Webb found is that the details of how quickly galaxies assembled in their earliest phases and what physical processes drove their early luminosity are not yet correctly captured by the models. The framework still stands, but the early chapters inside that framework are being rewritten. For the question of how many galaxies exist, these findings carry a specific implication that matters. The count of 2 trillion was built on models of galaxy formation and evolution. Models that use the observed populations at different epochs to reconstruct the full history of the galaxy count. If those models are not correctly describing the early universe, if galaxies assembled faster and shone more brightly in their earliest phases than the models predicted, then the reconstruction of the full population history is at least partly incomplete. In which direction and by how much are questions the astronomical community is actively working through. Every one of those early galaxies Webb is finding, every little red dot, every unexpectedly luminous structure blazing at the edge of the observable universe, is a data point that the count of 2 trillion was not built to include. Webb is extending the census back into territory that was previously blank on the map. And the territory is not blank. It was never blank. It was just waiting for an eye sensitive enough to read it. There is a particular kind of frustration that comes from working hard on a problem, making genuine progress, refining your methods and improving your estimates, and then realizing that the problem you have been working on is not quite the problem you needed to be working on. Not because the work was wasted. The work was real, and the progress was real. But, somewhere in the framing of the question, an assumption was embedded so quietly that nobody noticed it was there. And that assumption, once you see it, changes the nature of what you have been doing. The question is, how many galaxies exist in the universe? The assumption embedded in that question is that the universe is, in some meaningful sense, a knowable totality. That when we say the universe, we are pointing at something whose contents could, in principle, be inventoried. That the count has an answer, even if the answer is very large, and that the job of science is to get closer to that answer over time. That assumption is wrong. Not approximately wrong. Not wrong in a way that a better telescope will fix. Wrong in a way that is built into the physics of space and time. The observable universe has been expanding from a hot, dense early state for about 13.8 billion years. Since then, light has been traveling outward from every point in space at the same fixed speed, roughly 186,000 miles per second. You might expect this means we can see everything within 13.8 billion light-years of us. But the universe has been expanding the entire time that light has been traveling. When a galaxy emits light, and that light begins its journey toward us, the space between us and that galaxy is stretching. The light is moving toward us, but the destination is moving away. If the galaxy is close enough, the light wins. It crosses the expanding gap and eventually arrives. If the galaxy is far enough away, the expansion of space between us is faster than the light can travel, and the light never closes the distance. This is not a violation of the rule that nothing can travel faster than light. The rule applies to objects moving through space. Space itself has no speed limit. It can expand as fast as the physics of dark energy allows, which in the far reaches of the observable universe is faster than light moves through it. Galaxies in those far regions are not moving through space away from us. They are sitting still while the space between us and them stretches faster than light can cross it. The practical consequence is a horizon, a distance beyond which light emitted today will never reach us, no matter how long we wait, because the expansion is carrying those regions away faster than the light can travel across the growing gap. Anything beyond that horizon is not merely hard to see. It is causally cut off from us. No signal of any kind can ever travel from there to here. The observable universe, the sphere of space from which light has had time to reach us, extends about 46 billion light-years in every direction. It is larger than 13.8 billion light-years because the space that ancient light crossed has itself expanded since the light was emitted. The light we are now receiving from the most distant observable galaxies was emitted when those galaxies were much closer to us. And those galaxies have since been carried much farther away by the expansion of space. Beyond 46 billion light-years, the universe continues. There is no wall. There is no edge in any physical sense. The laws of physics that govern galaxies inside the observable sphere apply equally outside it. The dark matter and ordinary matter beyond our horizon formed the same kinds of structures as the matter inside it, following the same gravitational dynamics, assembling into the same kinds of galaxies and filaments and voids. There is almost certainly more of everything out there. We will never see any of it. The word never is doing serious work in that sentence. It is not standing in for probably not in our lifetimes, or not with current technology, or not without a major theoretical breakthrough. The causal structure of the universe, the physical fact that information travels at finite speed through space that is expanding faster than light in the most distant regions, permanently separates us from everything beyond our horizon. No improvement in instruments changes this. No theoretical advance removes it. It is a feature of the universe, not a feature of our limitations. And there is something else worth understanding about that horizon. As dark energy continues to accelerate the expansion of space, more galaxies will cross beyond the boundary from which any new light they emit can ever reach us. The sky will not suddenly go dark. It will empty slowly, one unreachable galaxy at a time. The part of the universe that can remain in causal contact with us is not growing. It is shrinking. All of our counts, the 200 billion, the 2 trillion, everything that every telescope has ever contributed to the census of the universe, applies only to the observable fraction, the portion inside the horizon, the part where the light has had time to arrive. The question, how many galaxies exist in the universe, when answered with a number like 2 trillion, is actually answering a different question. How many galaxies exist in the observable universe? The portion from which light has had time to reach us. That is a specific, bounded region of a larger whole. And the larger whole is where most of the universe almost certainly is. How much larger is the actual universe than the observable portion? The universe could be 10 times larger than what we can see. It could be 1 billion times larger. Some theoretical frameworks suggest it could be effectively infinite. Every measurement we make is, by definition, made within the observable sphere. We cannot measure what we cannot observe, and we cannot observe beyond the horizon that the physics of expansion has placed around us. 2 trillion, the number that became the headline answer, is not the answer to the question as it was asked. It is the answer to a smaller question nested inside the larger one. It is an inventory of one room when the question was about the entire building. And nobody knows how many rooms the building has, or whether it has an outer wall at all. The question how many galaxies exist in the universe has no answer that any being anywhere in the universe can determine. The galaxies are there, but there is no vantage point from which the complete inventory can be taken. That is what the question was actually asking, and that is what the physics actually says. Stand outside on a clear night and look up. What you are doing, though it does not feel this way, is looking into the past. The light from the moon left its surface about 1.3 seconds ago. The light from the sun, if you were foolish enough to look directly at it, left 8 minutes ago. The light from the nearest star beyond our sun left 4.2 years ago. The light from the bright stars you can trace into constellations left anywhere from a few dozen to a few thousand years ago. Some of those stars may no longer exist in the form you are seeing. They have had centuries to change since that light departed. And you would have no way of knowing. The Andromeda Galaxy, the smudge that Hubble measured in 1923, shows you Andromeda as it looked 2.5 million years ago, when that light left Andromeda. Our ancestors were early members of the genus Homo, walking across the African savanna, not yet using fire in any controlled way. The galaxy you see in the sky tonight is a 2.5 million year old image. The real Andromeda, in whatever configuration it has reached in the time since that light departed, is invisible to us. It will remain invisible for 2.5 million more years. When the light carrying its current image finally arrives, this is not a quirk of our instruments. It is the fundamental nature of observation across large distances. Light travels at a fixed speed. Distance takes time to cross. Every observation is a view into the past. And the further you look, the deeper into the past you see. For nearby objects, this barely matters. The moon, as it was 1.3 seconds ago, is functionally identical to the moon as it is right now. For galaxies at cosmological distances, the delay is so large that what you are seeing is not the contemporary universe at all. It is a layered archive, a stack of different eras, all visible simultaneously in the same sky, each distance corresponding to a different moment in cosmic history. The most distant galaxies that Webb has observed were seen when the universe was about 280 to 290 million years old. Those galaxies existed as they actually were, young and dense and energetic, in a cosmos just beginning to organize itself. What they are now, after more than 13 billion years of evolution, merging, and star formation, we cannot know. The light carrying that information is still in transit. It will not arrive for billions of years. When you count galaxies in a deep field image, you are not counting the galaxies that exist right now. You are counting galaxies that existed at various points across the history of the universe, all visible at once from our particular location in space and time, simply because their light happened to arrive here at this particular moment. The nearby galaxies in the image represent the recent universe. The faint, distant smudges at the edges of detection represent the universe as it was billions of years ago. These are not the same galaxies at different stages of development. They are genuinely different objects, in genuinely different eras, seen together only because of where we happen to be standing and when we happen to be looking. The 2 trillion figure is not a simple photograph of the universe at one universal present moment. It is reconstructed from observations spread across cosmic time, combined with models of how galaxy populations form, merge, fade, and evolve. It is a census built from light arriving now. But the light itself comes from many different epochs. Some of the galaxies counted in the deep field images have, in the time since their light left them, merged with other galaxies. They are no longer separate objects. Others may have been disrupted, their stars scattered into intergalactic space. The process of galaxy mergers has been steadily reducing the total number of independent structures since the early universe. There is no present moment at cosmic scales. This is the thing that is hardest to absorb about the observable universe. When you look at a galaxy 10 billion light-years away, you are not seeing it simultaneously with the moment you are standing in. Special relativity, established more than a century ago, showed that simultaneity is relative. For events separated by cosmological distances, the disagreement about what counts as now is not a small correction. It is profound. The observable universe is not a sphere of space. It is a sphere of space-time, a volume of the past made visible by the travel time of light. Its boundary is not a wall. It is a moment in time. The moment when the universe first became transparent enough for light to travel freely. About 380,000 years after the beginning. Before that, the universe was a hot, dense fog that light could not penetrate. The faint microwave glow that fills the sky in every direction. The cosmic microwave background is the oldest light we can ever receive. It is the furthest back we can see in the time direction. The earliest message the universe was physically capable of sending. Beyond that boundary, in the space direction, lies the rest of the cosmos. Those regions exist. They contain matter and dark matter and galaxies and all the structures that physics produces. They are simply and permanently outside the sphere of what any observer at our location can ever know. The edge of the observable universe is made of two things woven together. It is a distance in space, the farthest point from which light has had time to reach us. And it is a moment in time, the earliest epoch from which the universe was able to send a signal. The edge is where those two things converge. Stitched together by the speed of light and the age of the cosmos and the rate at which space has been expanding since the beginning. The galaxies we count are not a clean census of what exists at one universal now. They are a record of light from what existed, spread across time, all arriving at once, all telling their stories simultaneously to anyone patient enough to collect the light and careful enough to understand what the light is actually saying. At some point in any serious inquiry, you reach the place where the honest answer is not the satisfying one, where the most accurate thing you can say is also the most uncomfortable, where the question deserves a number, and the number does not exist in the clean form. The question seems to call for two serious, independent, carefully constructed scientific efforts have tried to answer how many galaxies exist in the observable universe. They used different methods, different data, different approaches to the same problem. They arrived at answers that differ by a factor of 10. The first is the estimate produced by Christopher Consolis and his team, built by studying how the galaxy population evolved across cosmic time, modeling the faint invisible galaxies that surveys could not detect, and extrapolating to a total population consistent with the observed galaxy counts at different epochs. Their conclusion was approximately 2 trillion galaxies in the observable universe. That number rests on models of galaxy formation and evolution, on assumptions about how many faint dwarf galaxies exist below the detection threshold of current instruments, and on the statistical methods used to extrapolate from the observable sample to the full population. The second comes from a completely different direction, out in the outer solar system, far enough from the sun that the faint haze of interplanetary dust that blurs sky measurements near Earth is essentially gone. The New Horizons spacecraft has been making observations from a position of genuine darkness. The team used New Horizons to measure the total brightness of the night sky, stripping out every identifiable source of foreground light and looking at what remained. What they were measuring is called the cosmic optical background, the combined glow of all the light in the universe that has reached this part of space, a faint and uniform illumination coming from every direction at once. The logic connecting that measurement to the galaxy count is indirect but real. If there are 2 trillion galaxies out there, all of them emitting light across billions of years, that light has to go somewhere. Some of it arrives here, contributing to the cosmic optical background. Add up the expected contribution from all those galaxies, account for the expansion of the universe that dims light as it travels across growing distances. And you can ask whether the measured background brightness is consistent with 2 trillion sources or with a smaller number. The New Horizons result, when analyzed this way, placed pressure on the higher estimate. The measured background glow was more consistent with a galaxy population in the range of several hundred billion than with 2 trillion. It is important to be precise about what this measurement does and does not say. The cosmic optical background is not a direct count of galaxies. It is a measurement of total light, and connecting it to a specific number of galaxies requires assumptions about the average luminosity of galaxies, the fraction of their light that has been absorbed along the way, and how the galaxy population has changed over cosmic time. Each of those assumptions carries uncertainty. The measurement constrains the possibilities. It does not close the question. So the situation is this. The 2 trillion figure says there must be many more galaxies than we can see to explain the patterns we observe across cosmic time. The cosmic optical background measurement says the total light arriving from all those galaxies should add up to a specific amount. And that amount is more consistent with fewer galaxies than 2 trillion. Both results are real. Both rely on assumptions that carry genuine uncertainty. The disagreement is not a flaw in the story. It is the story. The gap between the two numbers reflects different methods, asking slightly different versions of the same question, and illuminating different aspects of the same underlying reality. The concise estimate asks how many galaxies must have existed across all of cosmic time to produce the patterns we observe. The optical background measurement asks how much light is actually arriving from all those sources right now. Those are related but not identical questions. And the answers reflecting different things is informative, not contradictory. The honest current answer is a range. Several hundred billion at the lower end, supported by the direct measurement of arriving light. 2 trillion or more at the upper end, supported by models of the galaxy population we cannot directly observe. The true value somewhere in that range, with the uncertainty reflecting not sloppy science, but the genuine difficulty of counting objects that are mostly too faint to see, across distances so large that the light from them carries information about the past rather than the present. The most accurate statement that current science can make about the galaxy count is this. We know there are at least several hundred billion galaxies in the observable universe. There may be as many as 2 trillion or more when the ones too faint to detect are properly accounted for. And beyond the observable universe, in the vast regions from which no light will ever reach us, there are almost certainly more, in numbers that depend on the total size of the universe, which we do not know, and may never be able to determine. That is what knowledge looks like when it reaches the edge of what the universe permits anyone to know. And yet the work continues, not because the final number is within reach, but because between the numbers we cannot close and the questions we cannot answer, there is still an enormous amount of what can be understood. And one instrument in particular was built not to close the count, but to measure something the count had always been standing next to without fully seeing. On July 1st of 2023, a rocket lifted off from Cape Canaveral, carrying a telescope that was not built to look at individual galaxies. It was built to look at all of them at once. The Euclid Space Telescope, a mission of the European Space Agency, was designed to do something that no previous instrument had attempted. At this scale, map the three-dimensional distribution of galaxies across a significant fraction of the observable universe, charting their positions and distances with enough precision to read subtle patterns written into their arrangement by forces acting across billions of years. The mission target is to observe more than 1.5 billion galaxies over 6 years of operation. Not 1.5 billion deep exposures of faint, distant objects the way Hubble Deep Field observations worked. 1.5 billion galaxies catalogued, positioned, and incorporated into the largest three-dimensional map of the cosmos ever assembled. If you spent 1 second looking at each galaxy in Euclid's survey, you would need about 47 years to finish. The map being built is not a refinement of previous surveys. It is a different category of enterprise. But the thing that makes Euclid genuinely strange as an astronomical instrument is this. It was not designed primarily to study galaxies. It was designed to study something that is not a particle, not a star, not a galaxy, and not a substance anyone has ever held in a detector. Something known almost entirely. By the way, it changes the expansion of space. It was designed to study dark energy. Dark energy is the name astronomers use for whatever is causing the expansion of the universe to accelerate. In the late 1990s, two independent teams studying distant supernovae made a discovery that won the Nobel Prize in Physics in 2011. The universe is not just expanding. It is expanding faster and faster over time. Something is pushing space apart, overwhelming the gravitational pull of all the matter in the universe and causing the rate of expansion to increase rather than slow down. We do not know what dark energy is. This is not a polite acknowledgement of uncertainty at the margins. Dark energy constitutes roughly 68% of the total energy content of the universe, making it the dominant component of everything that exists. And no physical theory fully explains it from first principles. The cosmological constant, a term that Einstein introduced into his equations of general relativity, provides a mathematical description that fits the observations well enough. But a mathematical description is not a physical explanation. We know the effect. We do not know the cause. What we do know is that dark energy shapes the universe in measurable ways. It affects the rate at which galaxies move apart from each other. It influences how clusters of galaxies form and grow over time. It leaves a signature in the large-scale distribution of galaxies, a subtle pattern in how they cluster at different scales and different cosmic epochs, that encodes information about how the expansion rate has changed throughout the history of the universe. Reading that signature requires a map, a very large, very precise, three-dimensional map of where the galaxies are, how they cluster, and how their distribution has changed from the early universe to the present. Euclid is building that map. The galaxies are not the destination. They are the instruments. Each one is a data point in a measurement of something invisible that shapes everything they do. The galaxies are not the answer anymore. They are the measuring marks on the ruler. This is a profound inversion of the original project of counting galaxies. When Hubble pointed the 100-inch telescope at the Andromeda Smudge in 1923, the galaxies were the discovery. Finding them, measuring them, understanding what they were and how many existed. That was the scientific goal. The galaxies were the point. A century later, we are using galaxies as measuring devices to detect the imprint of a force we cannot see directly. The count is in service of a deeper question. That deeper question is about the fate of everything. Dark energy determines the long-term history of cosmic expansion. If it behaves as the current standard model suggests, like a constant background energy of empty space, distant galaxies will keep receding beyond one another's horizons. The observable universe will slowly empty out as more galaxies cross beyond the boundary from which light can never return. And the cosmos will grow progressively colder and darker over timescales that make the current age of the universe look like a morning. If dark energy is not constant but changes over time, the far future could look different in ways that depend on exactly how it evolves. Euclid is designed to test which version of that story the universe is actually following. By measuring whether the signature dark energy leaves in the galaxy distribution has remained consistent across billions of years or whether it has shifted, Euclid's first data releases came in late 2023 and early 2024, showing early glimpses of what the full survey will eventually contain. The initial images were striking not for their depth, but for their breadth. Where Webb shows you a tiny patch of sky in extraordinary detail. Euclid shows you enormous swaths of sky with enough detail to catalogue every galaxy in them. The first data release covered a fraction of the eventual survey area and already contained tens of millions of galaxies. Looking at those early maps, the cosmic web was immediately visible. The filaments and voids that surveys in the 1980s first revealed were present in crisp detail across regions of the sky far larger than any previous survey had covered. When the full 6-year survey is complete, the map will cover roughly 1/3 of the total celestial sphere. With galaxy positions and distances measured across a volume of the universe stretching back about 10 billion years, within that map, cosmologists will be able to measure the rate of cosmic expansion at different epochs with a precision that no previous survey has approached. They will map the growth of structures over time with enough detail to test whether dark energy has been constant throughout cosmic history or whether it has changed. There is something fitting about how the story of counting galaxies has arrived here. It began with an instrument problem. Nobody could measure distances, so nobody could determine whether the spiral nebulae were inside the Milky Way or far beyond it. The distance problem was solved by Leavitt's period luminosity relationship, applied by Hubble to Cepheid variables in Andromeda. Once distances could be measured, galaxies could be counted. Now, a century later, we are measuring distances not to count galaxies, but to measure the expansion history of the universe itself. We are using 1.5 billion galaxies as landmarks to track how space has behaved over the last 10 billion years. The galaxies are still the instruments, but now we know they are instruments. Now the measurement is conscious of what it is doing in a way that Hubble, staring at that glass plate in the cold on Mount Wilson, could not have anticipated. Euclid will not tell us how many galaxies exist in the universe. It will tell us how the galaxies that exist in the observable portion are distributed, how they cluster, how the clustering has evolved, and what that evolution implies about the nature of the force that is slowly pushing them beyond one another's reach. From that, it will tell us something about the future of every galaxy in the observable universe, including our own. How much time remains before the accelerating expansion carries more and more of them across the horizon? How long the sky will remain as full as it is tonight? That is the measurement that matters most now. Not how many galaxies there are. How long the light from one will be able to reach another. And the answer to that question is itself a number with an end. The October of 1923. A man in a cold, dark room on a California mountain writes a red exclamation mark on a glass plate and does not sleep. He has just found out that the universe is larger than anyone knew. He has measured the distance to a smudge in the sky and discovered that the smudge is not a local cloud of gas, but an entire separate galaxy. A structure containing hundreds of billions of stars, sitting millions of light years beyond the edges of the Milky Way. The immediate thought that follows is that the other smudges in the sky must be the same kind of thing. Thousands of other galaxies. The night sky suddenly full of a depth and a population that nobody had seen there before. He does not know, in that cold room, that the count he has just begun will spend the next 100 years refusing to settle. He does not know that a director will one day point his telescope at a blank patch of sky and find 3,000 galaxies in it, betting on the same thing. Hubble bet on that night that the universe had put something in the dark, and that a good enough instrument, held still long enough, would find it. He does not know that the multiplication of that image across the sky will produce a number 200 billion. That will feel like an answer for 2 decades before a team of astronomers shows that the vast majority of the real population is invisible. He does not know that the corrected estimate, 2 trillion, will arrive with its own set of unresolved questions about what exactly it is counting and whether the models that generated it are correctly describing the early universe. He does not know that a golden telescope will eventually be launched into space and find galaxies blazing in the early universe that looked more developed than the theoretical framework had prepared anyone to expect, forcing revisions not to the core picture, but to the details of how quickly the earliest structures assembled themselves. He does not know any of that. He knows that the Smudge is a galaxy, and he knows that the question of how many galaxies exist has just become real in a way it was not before. He has opened a door that will not close. 100 years of work have passed through that door. Optical surveys, radio surveys, infrared surveys, ground-based telescopes and space telescopes, photographic plates giving way to digital detectors, millions of galaxy spectra measured, distances calculated, positions plotted into three-dimensional maps of the cosmic web, deep fields pointed at blank sky and coming back full, estimates revised upward and then revised again. The darkness that Hubble saw beyond the edges of the Milky Way turning out to be not empty but densely, almost incomprehensibly populated. Layer upon layer of galaxies receding into the past, the further they recede into space. What do we know now? After all of that, there are really three questions hiding inside the one we started with. How many galaxies can we see? That answer improves with instruments. Current surveys have directly observed hundreds of billions. How many galaxies exist inside the observable universe? Including the faint ones we cannot yet detect. That answer improves with models. The best current estimate points toward 2 trillion, though the uncertainty on that figure is genuine and wide. How many galaxies exist in the whole universe? Beyond every horizon. In the parts of reality that the causal structure of space permanently withholds from any observer within it, that answer may not improve at all. It may never improve. The physics that places those galaxies beyond reach does not relax with better technology or sharper theory. It is a feature of the universe, not a feature of our limitations. 3 questions. 3 different kinds of answers. 3 different relationships between what we can know and what exists. We know the observable universe contains somewhere between several hundred billion and 2 trillion galaxies. Depending on which method you use to estimate the population that instruments cannot directly detect, we know this range reflects genuine uncertainty. Not about the galaxies we can see, but about the far larger population of faint dwarf galaxies that theory predicts and instruments have not yet reached. We know the early universe produced galaxies faster and more vigorously than the models predicted before Webb, and that Webb is still in the process of showing us what we missed. We know the galaxies are not scattered randomly through space, but organized into the cosmic web, a vast network of filaments and voids shaped over billions of years by the gravitational dynamics of dark matter. We know dark matter is the scaffolding on which every galaxy is built, the invisible architecture that preceded the galaxies and determined where they would form. We know the observable universe is not the universe. It is the portion from which light has had time to reach us in 13.8 billion years, bounded by a horizon set, not by any wall in space, but by the physics of expansion, the finite speed of light, and the age of the cosmos. Beyond that horizon, the universe almost certainly continues, containing more galaxies, following the same physical laws, organized by the same dark matter dynamics. We know that if the universe is infinite, the count of galaxies is infinite, and the question of how many galaxies exist has no numerical answer. The permanent part is what matters. Euclid will narrow the range within the observable universe. Webb will continue to constrain models of early galaxy formation. Better measurements of the cosmic optical background will sharpen the estimate from the other direction. The uncertainty about the observable portion will shrink, but the question of what lies beyond the observable horizon, in the regions from which no light will ever reach any observer anywhere in the universe, will remain open. The universe is structured in a way that places that information permanently outside the reach of any measurement from any location within it. Every observer in the cosmos, everywhere, is enclosed within their own observable sphere. No one gets the complete inventory. No one ever will. And here, in one of the galaxies that our instruments can reach, on a small planet orbiting an ordinary star, somewhere in an unremarkable part of a spiral arm, creatures assembled from ancient stellar debris have been pointing instruments at the sky and asking how many of these things there are. The answer they have found, after 100 years of looking, is that the number is very large, possibly infinite, definitely larger than observable, and that the edge of what can be known about it is not a temporary obstacle waiting to be overcome. It is a permanent feature of the reality they are trying to measure. Somewhere in the archives of the Space Telescope Science Institute, there is a record of a decision made in 1995. 10 days of time, a blank patch of sky, the same bet Hubble made again a lifetime later, by a different person with a different instrument. In the same faith that the universe had put something in the dark, it had. The glass plate with the red exclamation mark still exists, preserved in the Harvard archives. The smudge in Andromeda is still there, still sending its 2.5 million-year-old light across the dark toward anyone patient enough to look for it. The question that Mark opened is still open. It will always be open, and somewhere beyond the reach of every photon that will ever find us, galaxies we will never count are still forming stars, still merging, still going on without us. Not hidden, not imaginary, just unreachable. That is not nothing. That is almost everything.